All right.
What if we just...
We're good?
What if we just not do the proof? What if we just joke around for the rest of it?
We'll just make up some math and we'll
Yeah.
pass it out to them. Yeah, that sounds fun. No, we'll keep moving. So, hey everyone at home, you're not here, so John has volunteered to go ahead and film this, and he'll share it out with you guys. Okay, so we just talked, this is the idea of an equation of state. This shows us that quantities are set at a moment and that they don't necessarily show how you change from moment to moment, but they are connected from moment to moment. So the state here and the state there have a relationship. This works the same way. The pressure, the volume, and the temperature are true at a state. Now what I wanted to do before we move forward is two things. I need to first get R before I can do anything else, because I introduced this constant to solve this proportionality problem, right? So all that the gas laws told us were proportional relationships, we turned them into this. I should also define what an ideal gas is, so I guess there's three things in total. First, I want to get R, then I want to define an ideal gas, and then I also, if you guys want to see it, if it's not necessary, we can skip it, do an example of how you might use this combined gas law in a problem. So I guess let's do that one first. Do you guys want to see an example with this, or should we move on? It's a good one in the textbook. It's not that bad. Should I talk through what it would be, and then you guys can tell me if you would want to see it? So I think what I would probably pick to show the combined gas law in action would be to say that we have a balloon, and it is filled with a certain number of moles, and the gas cannot escape. And we bring it down to the atmospheric level or ground level here. So it would be under atmospheric pressure. I'd define some arbitrary volume for the balloon. I'd put it at room temperature. And then I'd say I'd let go of the balloon, and it's gonna reach some height in the atmosphere. And when it gets there, obviously the pressure will fall, the temperature will drop, and so the volume will change. And so I'd effectively ask you, like, using this, calculate the new volume of the balloon. I'd have to give you the start pressure, the start volume, the start temperature, the new pressure, the new temperature, that type of thing.
And multiply temperature over divide temperature.
Right, it's pretty trivial, yeah. You just multiply T2 over here and divide P2 down there. And I just have to make up a reasonable new pressure, being like 80% of atmosphere or something like that, and a reasonable new temperature. So that would be that. So can we just skip it?
Yeah.
Okay, cool. So that would be how you'd solve something like this. There's a good example in your textbook if you want to check it out. I'm looking at this phone like there's students there. There's a good example in your textbook if you want to check it out. And there's a couple problems on the first homework set about this. So if you have trouble with it, just let me know and we can go through these together. All right, so then let's come over here and let's try to get R. So R is the constant that makes this into an equation. And actually there are some conditions that we need to establish in order to kind of argue how this constant comes to be. And those are the rules of an ideal gas, which are four things, but I don't memorize all of these things all the time. I mean,
You
I can
expect us to know?
I do expect you guys to memorize them. And here they are. So let's list what makes an ideal gas. There are four conditions of an ideal gas. And if you read your textbook, they're quite lengthy, but I'm going to give you the paraphrased versions of each because that's all we need. It's the principles that it's built on, not an extensive structure of our language or something. So, okay. The first one, an ideal gas has many molecules moving in random directions with random speeds. So this actually isn't surprising at all. This is effectively what you would think of when you think of a gas. Many molecules all over the place, random directions, random speeds. Or another way, the shorter way to say random directions, random speeds is what?
Random velocity.
Random velocities, yeah? So, okay, the molecules have random velocities. Now, there is some average velocity amongst the molecules. But of course, velocity has a directional component to it, which means when you say average, it gets a little bit tricky. So we're actually going to learn about the root mean square today, which is a way to get around directional-based quantities that have averages. You'll see what I mean when we get there by the end, and if we don't get there by the end, we'll get there by Monday. So there is a way to deal with this random nature that kind of gives you an average behavior overall, even though the direction's also random, okay? The next thing is that we're going to assume that the average separation between molecules is much greater than the diameter of those molecules. The distance from molecule to molecule is much greater than the actual size of the molecules. And this is important because if the molecule's size was comparable to their separation, it means that they would hit much more frequently and they would get clogged up against each other, right? But because there's this large separation, the molecules are small compared to it, they get a lot of empty space between collisions. They get to move freely, and we get to then treat the collisions nearly as elastic. And that is actually the next condition. Oh no, that's the last condition.
Yeah.
The next condition says classical mechanics applies to each collision or to each molecule. Now you might be thinking that this means that we're saying they are not a quantum system in some way, that we're hinting at quantum mechanics because I'm using classical mechanics. But that's actually not what I'm trying to say here. Quantum mechanics would never have applied at the molecular level anyway, but quantum mechanics describes the way the electron interacts in its orbital. So quantum mechanics lives within an atom itself. So atom and atom interactions, quantum mechanics is less substantial. Obviously it can have some macro effects because it is a micro scale thing, and so some of those effects can manifest at the large scale, but this isn't about saying quantum mechanics is like somehow the better way to explain it. What this is really saying is that the kinetic energy of the molecules is much, much greater than the potential energy between them. Now, you haven't learned about electrostatics yet, but when you actually learn about it in chemistry a little bit, what you'll learn is that any molecule that has a charge is going to attract or repel another molecule. And so that charging, that attraction or repulsion, corresponds to some kind of energy stored in their configuration, right? You're used to thinking of this one. Here's the planet, here's a thing, and as you lift it up, that potential energy grows because the thing can now do more work by the time it falls, yeah? Well, that's because of attraction, which means electric charges, which are attracted, have energy in the same way. Or even electric charges that repel have energy that kind of wants to get them apart, and you have to hold them together, so you got to put work in to get them together. We'll cover that eventually. But what I'm getting at is all of those energy forms are potential energy. So we're basically saying they don't matter. And that's valid if they're not close. Because when objects are really close together, those electrostatic forces start to influence. You take a charged thing by a charged thing, they don't notice each other until they get to a reasonable range. So if they're separated pretty well, then the potential energy associated with their charges doesn't really matter so much. There's another thing that kind of is subtly hidden here, and that is, if you remember yesterday I talked about monatomic atoms and diatomic atoms. If you have diatomic atoms, then they can oscillate in their bonds. And that would be a form of potential energy stored in the oscillation. So we're going to ignore that too, which kind of means that we're saying we would like to be looking at monatomic atoms. Those would be better ideal gases. Now, we are going to kind of just treat most gases as ideal, even though that's not the case. But effectively, you can then reason this as also saying monatomic atoms. Because otherwise there'd be potential energy in their bonds, and that would matter. That would change the way they interact. There is another force that might cause potential energy, and that would be the nuclear forces inside the nucleuses. But like I just said, we're not going to allow any kind of nuclear collision to occur. So what's a nuclear collision? It's when you have an atom and another atom, and you get them close enough that their cores, their nuclei, can actually overlap. And when you spill those nuclei onto each other, the strong nuclear force gobbles them up into a nuclei, and it releases energy in the process. That's called fusion. We are not going to allow fusion to occur. So we're not going to allow us to reach those temperatures where that could happen. And so that would be another thing where the potential energy is low enough that really kinetic or motion dominates this work. Fair enough? And then the last condition is that the collisions themselves conserve energy. What's another word for that?
Elastic.
Elastic. So we're going to have elastic collisions. Okay? And with that, we can say that the time for a collision is much, much less the time between collisions. That is, when that gas molecule hits a wall of a container or hits another molecule, they are elastic, and so that collision doesn't have enough time happening for them to meaningfully deform anything. So deformation can't take place, the collisions are elastic. So in other words, the collisions happen very, very quickly. And then things bounce apart, and there's a long duration of time before they hit something else again, at least relative, right? Because if you actually were to track one molecule in a gas, it bounces off a surface, it's gonna hit another surface in fractions of a second. But the bounce itself is happening for even less than those fractions of a second. And so relative to each other, the collisions are happening quickly, okay? So these are my conditions for making an ideal gas. And they're kind of constraining because right here, this idea of monatomic means that you can rule out a bunch of very common gases for working well for this. But if you assume that these conditions apply to most gases, you can get a pretty good result. And that is actually where we're going to go and find R from. So if you wanted to take this formula, which we justified yesterday, we said, okay, this comes from the gas laws and the proportional relationships, and you wanted to get the constant value, all you would do is what?
Isolate for R.
You'd isolate for R, and you'd say PV over NT gives me R. And then that way you could solve it. Well, you would need to be able to measure all of these quantities, right? Which means you would need to have a gas with a known pressure on it, occupying a known volume, at a known temperature, and a known number of moles. Now actually, what you learned in chemistry is that 1 mole is built around a specific configuration of pressures and temperatures. Does anyone remember standard, STP, standard temp and pressure, STP? Well, this is just some choice that we've made for the normal pressure for a gas to be under and the normal temperature for a gas to be at. Well, if you recall, what's the normal pressure that we're all under all the time? 1 atmosphere. So the standard pressure is actually 1,100 or 101,300 pascals. I'm gonna write in standard units, newtons per square meter, because I'm gonna be doing everything in standard units. The standard temperature is actually defined as the freezing point of water, but in Kelvin. And so this is where I get to bring up something that I probably should have mentioned yesterday when I first introduced it, and that is how you go from Kelvin to Celsius. If you recall yesterday, we made the claim that minus 273.15 degrees Celsius is special. What's this called? That is absolute zero. And that is the point when theoretically motion stops occurring. Or if you like, kinetic energy disappears. So you've taken all the energy out of the molecules. That is the point when temperature cannot get lower. Because what is temperature? Temperature is a representation of kinetic energy. So if we're saying that we've got to the point where there's no motion, where there's no kinetic energy, we've got to the point where there's no temperature. Which means we should probably have a scale that starts here, yeah? And so the Kelvin scale starts there. So the way it works is Kelvin scale for temperature. And this is actually what we're going to be using going forward. The Kelvin scale says 0K, and actually, weirdly enough, when you're using Kelvin, we don't put degrees on it, we just say K. So this looks like okay, it's 0 Kelvin, yeah? 0 Kelvin is the start, and then we count up from there. But the Celsius scale isn't bad. It's built around water, right? So the size of the steps, 1 degree Celsius, 2 degrees Celsius, 3, those make sense to use from 0 to 100, 0 being freezing water, 100 being boiling water. So the size of a Kelvin is the same as the size of a Celsius. So if I say change of 1 degree Celsius, that is an equal to a change of 1 Kelvin. They are the same thing. Counting by Kelvin is counting by Celsius. It's just that Kelvin starts at 0, and then it counts up from there. So if that's the case, then what is 0 degrees Celsius in Kelvin?
273.15.
273.15. And that's going to be the standard temperature. So you can always get from Celsius to Kelvin by adding or subtracting this amount, 273. Now that means that we're defining the standard pressure as being here at ground level, atmosphere. We're defining the standard temperature as being freezing point of water, so that would be a cool fall day or a warm winter's day, right? Somewhere around there. And so that makes sense to call. But then the interesting thing is what we had found, or if you were go back to chemistry, if you are able to isolate 1 mole, and this is what makes a mole special, if you're able to get just 1 mole, so that is N equals 1 mole, then actually at standard temperature and pressure, all gases, well, all ideal gases, okay, all ideal gases occupy the same volume. And this is what made a mole special in the first place, is this notice, this observation that at this pressure, at this temperature, a specific count of molecules of any ideal gas has a certain volume. Anyone remember what that was? 22.4 liters. Now, there's some interesting ways to justify that this makes sense, but the best way to justify this one is to just say, experiment shows it. If you take a gas and you occupy 1 mole, you just get exactly Avogadro's number worth of molecules, and then you go ahead and put them under this pressure at this temperature, they will fill this much space. Okay? Now, that's only true for ideal gases. Now, you can get very close to this, and that would be then justified by it being a real gas. So ideal gases are what we work with, but a real gas deviates. And so effectively what you'll see as we go through this is we'll talk about this ideal gas concept, and then we'll get all these rules that apply to ideal gases, and then we'll just talk about a real gas deviates in this direction. Okay? And the reasoning for that is that the difference between ideal and real gas is this right here, all this potential energy, these diameters being inconsistent, these random directions having influence, so they're not truly random. All those things are factors that you can't easily quantify. And so we look at the ideal gas and then we say, okay, a real gas would work a little different. So if you did this for real with a gas, you might get 23 or 21. You get around this 22.4. But the most ideal conditions will give you exactly this. Okay, and actually this is what built a mole in the first place, which, by the way, since I'm at it, this is the first time we've introduced the mole proper, and this is a new standard unit. Remember in AP Physics 1, I told you there are 3 units? The unit of mass, kilogram, the unit of distance, meter, and the unit of time, a second. Well, the SI system actually has 7 in total. Does anyone know what the other ones are? Electric current, the ampere, the mole, which is actually different than mass. This is a count. Mass is a matter. It's how much matter, yeah? So we got those. Any more? We actually just listed the other one down here.
Temperature.
Temperature in Kelvin, that makes 6. And the last one is for dealing with light and the intensity of light, and it's called the candela, which we'll kind of dance around in this class. There's better ways to talk about the intensity of light than the candela, but it is defined as a standard unit. And so there are 7 standard units that all other units are built from: the kilogram, the meter, the second, the mole, the Kelvin, the candela, and then the ampere. So that's everything, okay? All right, so that covered, here we are. This is all the setup I had to do. And actually, with this setup, you'll notice, assuming that I did manage to get a gas at standard temperature, pressure, and I did intentionally get a mole of it, so that is Avogadro's number worth of molecules, now suddenly I can find R, yeah? I'm gonna encourage you guys to go ahead and plug these things in, but there is one issue if I plug all these values in as listed. One of these things is not the standard unit. The mole is a standard unit. The Kelvin's a standard unit. The Pascal's written in terms of standard units. What's the issue?
Volume.
The volume is written in liters. We need volume in what?
Cubic meters.
Cubic meters, yeah? So I'd like you guys to go ahead and find this volume in cubic meters real quick. Give it a shot.
100 cubic centimeters.
I assume that Jacob would show up late. He's just not here.
Jacob did shift physics, that's it.
How's the view on this thing?
It's alright. See the whole board.
Got it.
Is the writing clear?
Looks
I
like
feel
it.
like some of it's like
Yeah.
a bit clear.
Looks fine.
All right, here's our conversion. 22.4 liters over 1. We need to make it cubic meters. We know that a single milliliter is a cubic centimeter, yeah? So we need to get this to milliliters. And in fact, there is 1 liter for every 1,000 milliliters. And then we can go ahead and say, ooh, 1 milliliter is 1 cubic centimeter. And then we can go ahead and we can use, the ×3 process, which, if you guys recall, meant that we had to go ahead and put 100 centimeters over a meter, but we had to do it 3 times, yeah? So effectively, I could just save us a step and say 100 cubed centimeters cubed, and then 1 cubed meter cubed, yeah? That way it'll fit in the board. And so this would then give you, I think I ran this earlier, and I got 0.0224, and that would be cubic meters. So that is the space that a ideal gas occupies at standard temperature and pressure if you only have a mole of that gas. So I guess I should say 1 mole of ideal gas at standard temperature and pressure occupies this much space, which is actually relatively small, right? That is a cube that is, yay big. All right, so then let's go ahead and run the numbers on this. The pressure will be 1,300. The volume we just found is going to be 0.0224. The number of moles is 1, so that's nice. And then the temperature is 273.15 Kelvin. And this will give us the value of R in standard units. Now these numbers are rounded a little bit. The actual volume that I should get has a few more digits. The 273.15, that's pretty much what everyone uses, but technically it's like there's a 499999967 somewhere. I don't know. Who knows when it stops, but this isn't perfect. And then the atmospheric pressure is also less than perfect. So if these were all made perfect, you would end up with 8.314 as your answer. I think if you run these numbers, you get 8.307. So that 14 is the accepted value. This is what you would expect to see. Okay? What are the units on this going to be?
That's a good question.
It's kind of a mess.
Okay, yeah.
Yeah. So, okay, this is in what?
Newtons per meter.
So we have a Newton up top. We have a meter squared on bottom, yeah? This is in what?
Cubic meters.
Okay, so now we got 3 meters up top. In the bottom we have a mole, which is another standard unit, right? So far we're all metric. And then also what?
Kelvin.
Kelvin, okay. The Newton, the meter squared cancels a meter cubed, and we actually end up with a Newton meter, which is a special unit.
Joule.
It's a joule. This is a joule per mole Kelvin. So this, I should be writing it as 8.314 joules per mole Kelvin. So this is your ideal gas constant, written in terms of standard units. You probably remember from chemistry 0.821?
Yeah, 0.0821.
0.0821. That's what you get if you stay in liters and you write this in atmospheres. Okay? We're never going to use that, so why bother? Cool. So here is our ideal gas constant. Check. Now, here's the thing. I told you at the beginning of all of this that I actually would prefer to never talk about moles, even though, as I just defined, moles is a standard unit, and it has a place, right? I'm not ripping on the mole. It's a great unit. It's useful. But I prefer to think about particle count. And so I showed you the relationship yesterday. Does anyone remember what it was? How to get from moles to particles?
So like capital N over Avogadro or something?
I don't know. You guys wrote it down yesterday. I don't remember off the top of my head. I always got to then do the conversion again in my head, and I just wanted to avoid it.
Number of molecules, number over moles
let's see. Yeah, a mole
Yeah,
is in.
that's right.
It's
Capital
grams per mole, so you multiply grams per molecule.
Capital N over Avogadro's.
All right. Na. Let's make sure that works. Mole time grams per mole or molecules per mole. Yep, that works. Okay, so here's your connection. So what I'd like to do is take the ideal gas law and rewrite it to replace moles with capital N, number of molecules. And if you did that, you would end up here. PV equals capital N R over NA. I'm going to write it like this, times T. And the reason I'm writing it like that is because R is a constant and Avogadro's number is a constant. So those two constants become another constant. Yeah? And that constant gets a special name. It gets the symbol capital K, or actually K. And that is called Boltzmann's constant. And this one comes up all over the place. And this is what we'll be seeing quite often. This is my preferred way to write this. I hope to argue that this will also be your preferred way to do it. And when I eventually get into this fancy derivation that I'm working toward here, this is actually going to be part of it, okay? Now, let's quickly find the value for Boltzmann constant. How would you do it?
Plug.
Go ahead.
Just plug in R and NA.
Yeah, you plug in R, you divide R by Avogadro's number. And when you did that, you would take, R is 8.314 joules per mole Kelvin, and you would divide that by 6.022 times 10 to the 23rd. And what are the units on Avogadro's number? We used it to justify the original connection in the first place.
So stuff per mole.
Yeah, it's stuff per mole, or if you like, molecules is what I chose to use. Actually, you know what's a better word? I should have introduced it yesterday. Particles. Particles per mole. And MOL. So this must be this thing, Boltzmann constant, K, and you can run the numbers on that, and I believe you get 1.38. Can anyone double check for me real quick?
Yes.
Times 10 to the minus 23rd?
Yes.
Okay, 10 to the minus 23rd, and that is going to give you then, what are the units? Well, we are dividing by a fraction unit-wise, so we're going to multiply by the reciprocal, and so that looks like it's going to be, the moles will go away, and we'll have joules per Kelvin. Particle technically is a placeholder, so you wouldn't carry over the particle part.
It's like radians.
Right, it's a count of something. Just like radians are a count of, well, they're a ratio. Particles is what we write here, but really it doesn't mean anything, right? It's a count, so it's a number, it doesn't have a unit. So here you go, this is Boltzmann's constant. And that means that we now have everything we need to do the fancy proof I'm about to do. Let's begin.
I feel like we should delineate at least between Kelvin and Boltzmann to kind of listen.
Yeah, okay, well this is a unit, so I guess I could do this.
Okay, that's fair.
That would make it clear, right?
Yeah.
Fair point. And this is the type of stuff we run into a lot in this class. We've been running out of symbols since AP Physics 1, yeah?
Reinvent the alphabet.
Okay, so here's what I hope to prove from now until the end of the class on Monday, okay? So here's our hope to prove. Who knows what happens now? The original claim of all of this is that temperature is a representation of temperature. Here was just break for a second.
Shorthand.
That's an E. All right, great. Temperature is a representation of kinetic energy, specifically kinetic energy of molecules, or actually, new word, particles. Yeah. So this is what I'm going to attempt to prove. I'm going to attempt to show that temperature is directly proportional to kinetic energy. And here's another issue. In AP Physics 1, I used K, capital K, for kinetic energy. But now, capital K is the Kelvin. It's the Boltzmann's constant. So we're just going to be all over the place. So I'm going to write KE to avoid that. Fair enough? K. Spanish. What did you just say? K? Isn't that Y? Or is that what?
What?
It's what? Okay, cool. That makes sense then. Why? The ultimate question in physics. So let's begin. This is where we do kinetic theory. Now that's shorthand. It's really kinetic theory of gases, but whatever. Kinetic theory. This is the part that gets fancy. So here's what we're going to do. We're going to imagine we have gas sealed into a container. This container has uniform dimensions, making it the easiest possible container to explore. We're going to define the length of this container in any dimension as L. So it's a cube. And we're going to fill up this container with many, many gases moving in random directions with large separations between them such that the potential energy between them is negligible compared to their kinetic energy. In other words, I'm filling this up with what type of gas? Many, many molecules, random directions, random speeds, ideal gas, yeah? So we have this container of known size filled with an ideal gas. And I'm going to start by looking at the pressure applied to a single wall of the container. So let's take this wall on the right side. Here it is. And let's imagine a single particle coming in, hitting that wall, and then bouncing out. Particle, particle. Now it'll come in with some speed, but I need to look at this on a dimension by dimension basis. Otherwise it's going to get way too complicated, way too quick. So the trick here is going to be to look at the horizontal motion and then to extrapolate to all three dimensions by the end. So what I'm going to be interested in is the horizontal piece of the velocity. So that would be v naught x, and then the horizontal piece of the exit velocity, vx. And this particle will have a mass m. Now we know that this is actually an impulse problem. In AP Physics 1, you did a problem where you had a tennis racket and a tennis ball hit it and bounced off. That's basically this, yeah? And so what I'd like to do is specify the impulse that acts on the wall, specifically in the x direction. I guess I don't have to specify that because I'm going to use the x's, but I guess I'll say fx. Actually, it's impossible for this particle to push any direction other than horizontal on a wall like this, yeah? Because the wall pushes with a normal force horizontally, right? And Newton's third law says, okay, well, if the wall's pushing back that way, then the particle must have pushed in, right? So any up or down force along the wall are friction forces, and that would imply that the particle is going to skid, but these collisions are happening very quickly. It's an ideal gas, so it doesn't skid, right? There is no frictional loss here. This isn't the kind of wall that I'm looking at here. This is just the surface of a container. Particle hits and bounces and ricochets. So the force here has to be in the x direction, okay? And so then we can go ahead and say that force times the collision time for collision, must equal the change in momentum of that particle along the x direction. This is the impulse momentum theorem. The change in momentum of the particle is the mass times the final velocity vx minus the mass times the initial velocity v naught x. But I said that all the collisions have to be elastic in order for this to be an ideal gas, yeah? So if all the collisions are elastic, then that means that these two quantities have the same magnitude. There was no energy loss on collision. The initial velocity in x and the outgoing velocity in x are the same magnitude, but what's different about them?
Direction.
The direction. So we can say, oh, well, v naught x equals minus vx. Or move the minus sign over, doesn't matter where you put it, it's still the same thing. They're equal and opposite, yeah? Well, that means that I could go ahead and write v naught x as just put a minus sign, right? I could replace it here with a negative vx. So actually, I'll put the minus sign here. That'll make it easier. So where I see this minus v naught x, I can replace it with plus vx, yeah? And that means that the whole expression becomes force times time for collision equals m times 2 vx. Now, I'm inevitably going to be interested in the pressure of this container, because really when we're talking about gases, that's the way we quantify it, right? If you're on a particle by particle basis, this expression is great because, yeah, you can see the force that that particle imparts on a wall. But I'm interested in the holistic vision. I want to see all of it, which means I'm interested in the pressure on the system. So I'm going to rewrite this force as pressure. How do I do that? Oh, come on. Pressure is what?
Force over area.
Force over area, yeah? So where I see force, I can write pressure times length squared.
Oh, yeah.
T collision. Now this is where things are going to get a little tricky and hard to follow. This is the pressure as a result of a single particle's behavior. This is not the total pressure in the system. This is the pressure due to the collision from that one particular particle. Yeah? And specifically, this pressure doesn't last for long because the particle is not colliding for long. So if we were to stop here, you might say that there is a negligible pressure on the entire system because the particle hits, it leaves, and the pressure's gone. But that's not really what's happening because this is filled with gas, which means when that first particle leaves, what happens next?
Another particle.
Another particle is there to hit the wall, right? The pressure may only exist for an instant if I'm looking at a single particle, but when I consider there's many particles, the pressure continues to exist. There is a next particle to hit after the first one leaves. And so here's the clever bit, and this is one of the trickiest things to follow. If you consider that one particle I was just talking about, when it hits and leaves, well, it's going to be moving with this speed, at least horizontally. That's all I'm going to be worried about right now, with Vx. And it has to cross to the other end of the container and then return. So the velocity is going to be 2 times L over the time to return. So it bounces off, it hits the other side, it comes back. And so that horizontal velocity is just twice the distance it traveled, right? Or I should say the distance it traveled, which is twice the length, went across and back. And then it took some time to do that. Now, the argument I made before is that if I just stick with this time right here, then I'll be getting a pressure that isn't valid because that pressure ceases to exist after this time is up. But we know that the pressure persists because there's a gas in there. So the pressure must still be there, yeah? And so here's the argument I'm about to make. When the first particle leaves, there is some particle that fills the space. And then when that leaves, there's another particle that fills the space. And then when that leaves, there's another particle that fills the space. And this keeps happening until how much time passes? Until the particle that first hit comes back. So effectively, for the entire duration, this time t return, there has been a particle hitting this spot. It's just not been the same one particle. It's been a particle to replace its effect. Which means I can go ahead and realize, oh, the impulse wasn't acting over the collision time of a single particle, it was acting over what time? The return time of the particle. That's the duration of time across which all of the particles were hitting the wall. Okay? And so that means that if I go ahead and replace t collision with t return, I can get somewhere. Now I can only do this if I make that argument. So let me see if I can put it into words in the most succinct way possible. This is kind of hard to say. After the first collision, another occurs continuously. Until the original particle returns. Which means effectively, the impulse time is that return time. And that takes us to this point now. I can go ahead and solve this for t return and replace it right here. So I'll have p L squared, and then replacing t return, I will get 2L over Vx, and that's going to give me m2 Vx. The 2's will cancel. The L squared and the L, what does that look like? That's a volume. And actually, counterintuitively, I'm not going to keep the pressure and volume on the same side right now because I want to make some arguments about this pressure itself. So I'm going to go ahead and bring us to this point. The Vx can come over. I'll have an m. I'll have a Vx squared. You can already see the formings of kinetic energy emerging, yeah? A mass times a square velocity. We're just missing the 1/2, and this Vx isn't quite perfect because it's not the true velocity of the particle, it's only a component, but we're getting closer. And then, like I said, this L squared and L make a volume, which I'm going to divide over, and to delineate between velocity and volume, I'm going to write the volume like this, which is not the best symbol because this is actually what I use for voltage, but hey, we'll be all right. We don't know voltage yet, so whatever, okay? So this will be where I pick up on Monday, and if you can buy this part, then the rest of it's not so bad, all right? Ooh, I guess I should say one thing while it's fresh in mind. I know the bell just rang. You might consider this then, right here, this pressure, to effectively be the average pressure exerted on the wall considering the effects of one of all of the particles. I haven't considered the effects of every particle because what I've said here is that a particle hits and then its spot is replaced by the next. So that's only enough space for one particle to hit. So this is the pressure, on average, created by a single particle. We need to get the pressure in total from all the particles. And that's where we're going to go next. Okay? All right, guys. Thank you. Have a lovely weekend. I'll see you on Monday to finish this mess of a derivation.